uh, if we combine the two hydrogen orbitals in a linear combination, and to form a molecular orbital and try to solve a Schrodinger equation, we expect to get two molecular orbitals, one that is a bonding molecular orbital and one that's an anti-bonding molecular orbital. Okay, so we assume that the molecular orbitals of hydrogen are obtained from a linear combination of the hydrogen atomic orbitals, and by putting it into Schrodinger's equation, we would expect to get star, so it's the second orbital, and we call it sigma star, to emphasize that it's an anti-bonding molecular orbital. Okay, now so let's call these 1s. Let's look at the energies. So what are the energies of the molecular orbitals of hydrogen like? So let us say the hydrogen 1s orbitals. So let's just label the orbitals as 1s. So in the individual atoms, you have 1s orbitals of hydrogen. So in the separated hydrogen atoms, you have, let's imagine separated hydrogen atoms having singly occupied 1s orbitals. And let's consider this to be the zero of energy, where the atoms are infinitely far apart. So, as we saw, the orbitals could combine additively, or what we say in a constructive way, to form a bonding molecular orbital. When that's the case, the energy of the system is lowered. So when the 1s orbitals come together to form a bonding molecular orbital, the energy of the resulting bonding molecular orbital is lower compared to the energy of the original atomic orbitals. So the first orbital, the bonding orbital, is sigma 1, and we say the energy is lowered by the formation of this bonding orbital. Okay, so the bonding molecular orbital is lower in energy than the original atomic orbitals. Now, the anti-bonding molecular orbital, since it discourages bonding and actually causes the nuclei to repel each other, or the two atoms to repel each other, would be expected to be higher in energy. And in fact, it is higher in energy by the same amount. The bonding orbital is lower in energy than the original atomic orbitals. Okay, so the each bonding molecular orbital is lower than lower in energy than the isolated atomic orbitals, anti-bonding molecular orbital is higher in energy than the isolated atomic orbitals, and the bonding molecular orbital is lower in energy than the isolated atomic orbitals by the same amounts as the corresponding bonding atomic orbitals is higher in energy. Okay, so basically the diagram, the molecular orbital diagram for a molecule is symmetric. The bonding molecular orbital is lower in energy by the same amount as the corresponding anti-bonding molecular orbital as is higher in energy. Now, when you form a molecule, the electrons in the molecule will be assigned to the molecular orbitals in the same way you assign the atomic electrons into atomic orbitals. So remember that when you assign the electron configurations for atoms, you place the electrons into the lowest available atomic orbitals, right? So you filled lower energy atomic orbitals before you go on to higher energy atomic orbitals. So basically following the off-Bohr principle. And you also respect Hund's rule, in which if you have multiple degenerate orbitals, you have to put in the electrons into separate boxes with the same spin, right? So when filling in the molecular orbitals in molecules, the same principle applies. So for example, you have two electrons in the hydrogen molecule, and the electrons will go into the lowest energy orbital available. So the two electrons in hydrogen, they would go into which orbital in this case? Anybody?
Can you repeat the question, please?
The two electrons in a hydrogen molecule. So remember hydrogen molecule, H2 contains two electrons, right? Two valence electrons, right? In this single bond, right? In the molecular orbital diagram, where would we put the electron pair? In sigma 1 or sigma 2 star?
Sigma 1?
Yeah, exactly. Right? Correct, yeah. So you have two electrons, and they would both go into the lowest energy available orbital, which is a sigma 1 in this case. And each orbital can, remember, house a maximum of two electrons. So your pair of electrons in a hydrogen would go into sigma 1. And sigma 2 star would be empty, as expected, right? Because your hydrogen molecule is stable. And this means that the electron pair in hydrogen must be in an orbital that holds the nuclei together, and that would be sigma 1, right? You should not see any electrons in anti-bonding orbitals in stable molecules, because anti-bonding orbitals cause the atoms to fly apart. So if your molecule is stable, as is the case for H2, then we expect that both electrons would go into sigma 1. And certainly that's the case here, if we did the molecular orbital diagram correctly. Okay, so did you have something to say? Or no? Okay, so that's for hydrogen. Now, since this is an organic chemistry course, our interest, of course, is in organic molecules. So let us now look at the case of ethylene or ethene. Okay, so in the Lewis picture of ethene, we have two carbon atoms that are double bonded with each other. Well, actually, I drew it already, so I don't need to. I can just go back to a previous. So remember, in the Lewis description of ethene, you have two carbon atoms that are linked together by a double bond, and single bonds connect the carbons to hydrogens, right? In the valence bond description, you have a sigma bond between the two carbon atoms made by the overlap of sp2 hybrid orbitals. Sigma bonds between each carbon and hydrogen, also involving overlap of the carbon sp2, but with the hydrogen 1s orbitals. And then you have a pi bond consisting of overlap of the p orbitals. And for some reason, I'm missing a pair of electrons over there, so I should, well, too late right now. Yeah, so there's also a pi bond, which is located above and below the plane of the molecule, and it forms from sideways overlap of the p orbitals. So how would we view the pi bond in ethene? So we can use molecular orbital theory to describe specific types of bonds. And in the case of ethene and its reactivity, we're primarily interested in the pi bond because that's the bond that's involved, for example, in electrophilic addition reactions. So what would the pi bond in ethene look like when described with molecular orbital theory? So the pi bond is made up of the carbon 2p orbitals. So let us show the carbon 2p orbitals. So the carbon 2p orbitals, remember, they're dumbbell shaped. And they have, the two lobes have opposite phases, right? So this is a carbon 2p orbital. Now we have another carbon 2p orbital. And just like in the case for the 1s orbitals for hydrogen, we can imagine adding the two orbitals to form one orbital and subtracting the orbitals to form another. Okay, so if we add the two orbitals, then we get this molecular orbital. So the two identical phases constructively interfere, so they add with each other. And remember to emphasize the carbon atom is at the carbon nucleus is at the middle, right? In each atomic orbital. So when we add, what we expect to see is we expect the red part to sum together. And the blue part to also sum together. And the carbon atoms are in between. Okay, so we say this is a pi molecular orbital. And we say it's pi 1. And this molecular orbital is also bonding. So it is a bonding molecular orbital because there's a heightened electron density between the two atoms. Even though it's above and below the plane of the molecule, there's still a electron density in the region located between the two carbon atoms. So this helps glue the two carbon atoms together. So this is a bonding molecular orbital. Now, what happens when we subtract? So what does subtract mean? So based on what you remember from what we did with the hydrogen 1s orbitals, what do you think subtracting would look like in this case? Anybody?
Well, there's still gonna be that area where electrons can't go, right?
Yeah, but how would we subtract? Think, see if I can go back. How did we subtract in the case of the 1s? We added different colors, right?
Yeah.
So here, how would we add different colors?
Would we flip them?
We would flip one of them, right? So what we would do is we would, instead of subtracting two identical colors, we would add, but now we're adding opposite colors. So the red is added to a blue, and blue is added to a red.
Sir, just for clarification, what's the difference between the red one and the blue one?
The phase is different. Yeah, so it's like f of x is equal to sine x. So it's so f of x, if your function is f of x is equal to sine x, let's say, then f of x has positive values. That the function f of x has positive values when x is 0 to pi, right? And negative values when pi is when x is pi to 2 pi, right? Am I right? So the color represents the sign of the function. Is it positive or negative? So that's why when we subtract, we add the opposite sign, right? That's like subtracting, right? Adding a negative is like subtracting, right? Doesn't that make sense?
Yeah, that makes sense.
Okay, so what's the outcome? So the outcome, of course, is destructive interference. So you have your carbon atoms, but now you have something that looks like this. So you have a concentration of red on opposite sides, and a concentration of blue on opposite sides. And again, there's a region of no electron density, 0 electron density, between the two carbon atoms. Okay, so you have a nodal plane between the two carbon atoms where there's no electron density. And this is an anti-bonding molecular orbital, right? Because it places the electron density away from where the electrons could help glue the nuclei together. So in fact, the positively charged nuclei are rather repelling each other. So they would, this type of orbital would encourage the nuclei to fly apart. So that's why we call it anti-bonding. So this is pi 2. And we call it pi 2 star because it's an anti-bonding molecular orbital. Okay, so what would the energies look like? Okay, so thinking of the energies, your pi molecular orbital is constructed from the carbon 2p atomic orbitals, right? And again, the same principles that we outlined for the hydrogen case apply to the ethene case. So in the case of the pi molecular orbitals in